In this video, we're going to talk about linear models. The word model implies that we have some data or some information that we've gathered from the world around us in some way, and we would like to fit an equation to that information, to that data. So you can do that for a line, you can do that for lots of different types of functions or curves. And that's kind of the crux of what this college algebra course is about. It's to teach you about all the different types of functions with the goal of fitting those functions into everyday life. Okay, so for today, we're just looking at lines or linear models. So our goal is to find an equation of the line that comes the closest to passing through all of our data points. So we have some data points that we've collected from various places, and we would like to find a line that fits that data if it's possible. Okay, and then we're going to talk about two categories of information. So we may have some data that is exactly linear. So that if we were to plot these data points, they would lie exactly in a line, right? They're already set up in a linear pattern. And so we've talked about the patterns for linear functions, so we're just going to kind of reiterate that here again. And may not use the exact same words, but basically we have a uniform or a steady change in x that produces a constant or a steady change in y. Right? So uniform here means the x's are evenly spaced, and then if that's true, then there should be some pattern that we see in the y values as well. Okay, and when the idea of a first difference, this is basically the change in y. So if the change in y is always the same, the word constant here implies something that's always the same. So if the change in y is always the same, then we know that it's a linear function. Okay, we want to show you what that looks like. So I want to give you an example of exactly linear. And when it is exactly linear, we are going to do everything we've been practicing up to this point and find the equation of the line algebraically by hand. That's what you're going to be asked to do on a test and so forth, and that's good practice. Okay, so this example talks about postage. It says the table below gives the U.S. postage rates for first-class mail. Each weight is the largest weight for a letter mailed for that postage amount. Find a linear equation that will model this data. Okay, so we want to decide, first of all, when we have some data, is it exactly linear or approximately linear? Now we're dividing it up to make it very clear, but you're going to want to be able to make that decision in the future. Okay, so we want to look at your table. The first question is, are the x's evenly spaced? And I think we can all agree that they definitely are in this example, right? We have the weight in ounces, starting in 1, going up by increments of 1 ounce up to 5. Okay, the second question you want to ask yourself is, do I have a steady change in y? So I have a steady change in x. Does that produce a steady change in y? So to go from 42 cents in postage to 59, I'm going up by how much? 17 cents. Okay, to go from 59 to 76, I'm going up by how much? 17 cents. This is looking good. To go from 76 to 93, you guessed it, 17 cents. And to go from 93 to $1.10, 17 cents again. So this is how we would know that something is exactly linear. If we have a steady change in x, that produces a steady change in y. Okay, so now that we've decided it is indeed exactly linear, now we would like to find a linear equation that will model this data. And we've been practicing that. So in order to find an equation for a line, linear here implies that it's a line, we need two things. We need the slope and one point. Well, remember back when we talked about what the slope is the change in y over the change in x. I'm going to use that because we've already identified the pattern in the table. But if you wanted to choose any 2 points off this table and use the formula to calculate the slope, that would work also. We've already seen the change in y is 17 cents per each 1 ounce that we're increasing. Okay, so our slope is 17. And now we would like to find the equation of a line. So you want to maybe pick one point from this chart. I'm going to pick the first point, not for any good reason. Any of these points would work the same and give you the same answer. Okay, and then at this point, you want to choose which tool you want to use to find the equation of a line. You can use either, let me list them down here, y equals mx plus b. Plug in all of this information and solve for b. Or the point slope form, y minus y1 is equal to the slope times x minus x1. Hopefully you've been practicing with those and you've made a choice on which one you like better. That's what I would recommend, and kind of stick with the one you like so that you don't have to guess about it when you're taking a test or anything like that. Okay, so I'm going to use the mx plus b this time just because I think that's usually what you guys prefer. But either method works just as good. And I'm going to plug in the point I chose from the table. I'm going to plug those values in for x and y, and I'm going to plug in my slope for m. So since I chose that first point, y is 42, m is 17, x is 1, and I'm looking for the value of b. So 17 times 1, that's just 17. And I want to get b by itself, so I'm going to subtract 17 to the other side. So it looks like b is going to be 25. Okay, so now I want to put all that information together because I have my b and I have my m, and I want to make it into an equation of a line. So y equals 17x plus 25. We didn't really define our variables here, but x here, of course, represents the weight, and y here represents the postage. Now, if you wanted to change that, you could use w for the weight, p for the postage, however you want. But the equation, the format for it would look like this. Okay, so that's exactly linear. We talked about how to decide if it's exactly linear, and then this is sort of a reminder about the process that we would use to find the equation of a line or a linear model. Alright, so that's exactly linear. The next thing we want to talk about is when it is approximately linear. So sometimes our data points line up exactly in a line, like the postage example. We didn't make a graph for that, but we could have, and the points would have been equally spaced. But there are some times when the data does not line up perfectly. I mean, I think that would probably be the majority of the time in real life, right? So in that case, maybe the data we have is approximately linear. It could also be nonlinear, and we're not really going to talk about that today, but that is a possibility. If it's approximately linear, the scatter plot, if we were to draw a graph of just the data points, they should sort of cluster around a line. So what does that mean? That means maybe they don't line up exactly, but there looks like there might be a linear trend, right? There's sort of a trend here that the data is going up as it goes to the right for this particular sketch, okay? So it may cluster around a line. And since they don't lie exactly on a line, we may still have a uniform change in x. Usually the x is something we can control, and so we can maybe, whatever science experiment we might be planning, right, we control how often we collect the data. Anyway, usually the x is very easy to have a uniform or a steady change in x. But then when we look at the y, because it's not exactly, there may not be an exact change in y, right? So we use the word nearly constant, okay? So maybe it's in the same ballpark, but it's not really the same number increasing or decreasing each time. Okay, so that would be approximately linear. When we have a data set that's approximately linear, we're going to use what's called linear regression to find the equation of a line. And this is there are lots of ways to find a line that will approximate the data you have. It can't be exact because they don't line up exactly, but we can find a line that comes close. Remember our goal at the very beginning. So the regression line is one option. It's not the only option, and there are lots of other possible lines that you could use, but this is the one that we're going to talk about in college algebra. Okay, so I want to give you a little bit of explanation of what the regression line is. To do that, we need to talk about what's called the sum of squares error. Okay, and I'm not going to test you on this, but I just want to give you an idea of what it is so you can have kind of at least a basic understanding of what the regression line is. So there are lots of different types of error measurements as well. This topic in itself is sort of a baby step in the direction of statistics, okay? So we're definitely not going to dive into all of the statistics has to offer, but we're just going to give you a little bit of a taste of what's going on here. So an error measurement, right, is a way to measure how well your equation or your line fits with the data points that you have. It's not going to fit exactly because we're dealing with something that's approximately linear. So we want to have a way to measure how far is our data point. If it's not on the line, how far away from the line is it? So the way the sum of squares error works is we look at a point comparable to our data point that's vertically has the same x value on the line compared to our data point. And then because the y values are different, we subtract them. So we get this little vertical distance that we're measuring. So some of these points are above the line, so we would subtract and we would get a positive value for this distance. Some of the points may be below the line, and so we would get a negative measurement for the distance when we subtract it. So we don't want the positive distance and the negative distance to cancel out, right? We want to get a sort of a conglomerative estimate of the error we have. And so the sum of squares error takes those little distances by subtracting, that's how we get the distance, and squares them so that they're all positive and adds them all up. Okay, so that's one way to measure an error. It's not the only way by far, but it's one way. Okay, and the regression line is based on this type of error measurement. Okay, so maybe the main point of what we're trying to say here is the regression line is the line with the lowest possible sum of squares error. So we have our points are as close as we can get to the line. And the regression line is sometimes called the least squares line. Sometimes it's called the line of best fit. You might see those in the book. Okay, those are the same as the regression line. So the cool part about the regression line is that there are some formulas, but all of the formulas that we need are programmed into our calculator. And so we're going to take our calculator and use that to find the regression line. Okay, so if you have your calculator today, I'm pausing here because I don't have my calculator with me right now. I need to go get it. I may have to stop the video. To find the regression line, we're going to do two major steps at the beginning here. First, we need to enter the data. So we're going to do an example from the book, but let me just outline the steps here so you can start thinking about how this is going to work. We're going to use the stat key, which is usually in the middle of your calculator. And now I'm referencing a TI-84 or a TI-84 Plus. If you have a different kind of calculator, you may have to go look up the steps to do this. Okay, so we're going to use the stat key. It's kind of in the middle of the top section. It's right to the left of the left arrow. And then we're going to hit, there are some menus in all caps at the top. We want to choose the Edit menu. And the first choice in that menu is also Edit. Okay, and when you do that, so stat, you'll see the edit menu is the first menu, and you'll see one saying edit. You can either hit 1 or enter, and you will then see some lists. We're going to use the first two lists, list 1 and list 2. So we want to enter in our X's in list 1, and we want to enter in our Y's in list 2. Okay, so this will allow us to take an example and put all the X's and all the Y's into a table. And we're going to do that in just a second. The second step is to actually perform the linear regression. So once we have all of our data typed into our calculator, we're going to go back to the stat key. Okay, we're going to arrow to the right for the calc menu at the very top. And then we want to choose the fourth choice in that menu, which is the linear regression. Okay, now my calculator is kind of old, so when I choose linear regression, it puts that command on my screen and I hit enter. For some of you with a newer calculator, you might need to scroll down all the way down to the bottom of this sort of screen with a list of stuff and hit calculate. So I'm going to write both of those here because it'll depend on the age of your calculator. Okay, so there are more steps that I'm going to add to this list just so that you can see the graph, because it is a graphing calculator. That's kind of the benefit. But for right now, let me give you an example so we can practice these two steps. Okay, so here is, why don't we do it like this? No, that's not going to work. Okay, we'll just go with this. Alright, so here's an example from your book. It's about bottled water. It says the table below gives the per capita consumption in gallons of bottled water in the U.S. So how much we drink per year. Find the best linear model for the data. So we want to first, I guess, maybe let's ignore this for the moment. We want to check to see if this is exactly linear or approximately linear. I think we can see that the years are lining up in a steady fashion. If we check the bottled water, the gallons here that we're drinking, this is going up by, what is that, 1.3? No, 0.7. Okay, and to go from 28.3 to 29.2, this is going up by 0.9. And then the next one is going to go up by 1.6. And then to the last one, we're going up by 1.2. Okay, so we can definitely see, because the change in Y is not the same for each of these, that it is approximately linear. And that is how we're going to decide to use linear regression. If it's approximately linear, we're going to use linear regression. Okay, now it is sometimes convenient to make a little bit of an adjustment to the X values, especially if the X value is a year. Because 2009 is such a big number, it might be good to let X represent the number of years after 2009. And this is a very common thing to do. It'll make our equation a little bit more manageable. So what this means is we're going to treat 2009, because that's the first data point we have, as like year 0, right? We're just starting our experiment. We're at the very beginning. This is the initial amount, the starting amount, and 2009. And then we kind of count on from there, right? Since 2010 is the next year, 1 year later, we're going to let it be 1. It's 1 year after 2009. 2011 is 2 years later. It'll be a 2, right? And so forth. Okay, so take a second and go back with your calculator and enter this data into your calculator.